What is a function? It's an algebraic rule that takes an input and gives an output. The notation for a function is the name of the function, which is usually small letters such as f, perhaps also g can be used, or h, or perhaps short words that are used as the names of the rules. Then a variable follows next between parentheses. That indicates what is the variable or variables in terms of which the rule will be enunciated. And then the symbol of equality and the definition of the rule, which is a compound algebraic expression that involves the use of the variable that appears between parentheses. For example, in the question below, they give us a definition of a function first. It says if f of x equals to x plus 1. So here, this equality is actually a definition. The left side of the equality contains the name of the function, in this case f, and the variable in terms of which this function or rule is defined, variable x. And what you find on the right side of the equality is the definition of the function that is an algebraic rule in terms of x. In this case, the operations 2 times x plus 1. The question says here, what is f of a plus 1 in terms of f of a? So how do we interpret, after we see the definition of some function, what does it mean, the name of the function accompanied by some expression between parentheses next to the name of a function? Well, it can mean either of two things. Perhaps if the expression is a value, that is a number, then it means that you have to substitute that value wherever the variable appears in the rule and do the operations. So in case the expression is simply an algebraic expression, that is, you need to substitute that algebraic expression wherever the variable appears in the definition. Let's see an example. If we see, for example, f of 5, if we take this as our sample function, then according to the definition, this expression would mean to replace 5 where x appears and then operate it likewise, following the same sequence of operations. We would do 2 times 5 plus 1, and that would be 11. So to see this expression, f of 5 implies simply the value 11, because that is what you get as the output when you have as input the value 5 in the place of the placeholder variable x. Now, what if, for example, you see this expression, f of 1 minus 3 times y? How do we interpret this expression? Well, again, this makes reference to the output of evaluating this rule 2x plus 1 using as the value of x, not a numeric value, but instead the whole algebraic expression 1 minus 3y. So if we substitute where x appeared, you would have to multiply 2 times 1 minus 3 times y, and then add 1. But of course, if you simplify a little bit, reduce like terms, and the like, you would have 2 times 1 equals 2, 2 times negative 3y, that is negative 6y, and plus 1. So in the end, this is 3 minus 6y. So you see, to see this under the definition of f as the function in the question would imply the algebraic expression 3 minus 6 times y. That is to say, whenever you see this notation in the GMAT, that always refers to the output of a function. That is the results of evaluating the rule defined by the function using as input whatever appears between parentheses instead of the placeholder variable in the definition of the rule. So let's follow the same idea. F of a plus 1 should be 2 times a plus 1 plus 1. And f of a will be 2 times a plus 1, following the same definition for function f. So the question is actually, what is 2 times a plus 1 in terms of 2 times a plus 1? Since this expression can be rearranged as 2 times a plus 1 plus 2, you might say that because 2a plus 1 can be represented by saying f of a simply, the question may be responded like this. F of a plus 1, that is to say, 2 times a plus 3 equals f of a, that is 2 times a plus 1 plus 2. Because you know that this is 2 times a plus 1. And you know that this, it's 2 times a plus 3. So that's a possible question. Another possible question might be to evaluate certain operations with the output of the function, but with numeric inputs instead. For example, if f of x equals 1 over x plus 2, a question might be, what is f of 5 minus f of 3? According to the definition, f of 5 would be 1 over 5 plus 2, and f of 3, 1 over 3 plus 2. In other words, 1 over 7 minus 1 over 5. And the answer would be negative 2 over 35. Let's see a few examples of questions with functions in the GMAT Quant. Skip some questions. Let's try question 3. For every positive integer x, f of x represents a product of all even integers from 2 to x inclusive. For example, f of 10 equals 2 times 4 times 6 times 8 times 10. What is the greatest prime factor of f of 28? So we see this definition for function f is given in terms of a description, the product of all even integers from 2 to x inclusive. And we are given an example just to visualize what this definition works like. F of 10, for example, would be the product of all even integers from 2 to 10. And we're asked what is the greatest prime factor of f of 28. F of 28, as per the definition given, would be 2 times 4 times 6 times all even integers from 2 to 28. So including 22, 24, 26, and 28. So this would be the expression for f of 28. And now the question would be, what is the greatest prime factor of this numerical expression? Since we agreed that an expression like this, where you see the name of the function and some input between parentheses, means to replace that input, whatever it may be, a numerical value or an algebraic expression, in the definition of the rule. Since it says f of x represents the product of all even integers from 2 to x, this means the product of all even integers from 2 to 28. But this is a huge number. And of course, a product of many integers has a lot of prime factors. Why? Because each integer has a number of prime factors itself. For example, 6 is the product of 2 and 3. So can you say that 3 is a prime factor of this whole product? Obviously, you can say so. 3 is a product or is a factor of 6, so 3 is a factor of the whole product, which is, or which we call f of 28. So what is the greatest of prime factors available within the factors in this product? You can see that 22 has 11 as a prime factor, which is greater than 3, obviously. 24 is only made up of 2s and 3s. But 26 has a greater factor. 26 has 13 as a prime factor, while 28 doesn't have a greater prime factor because it's only made up of 2s and 7s. So in the end, the number 13 would be the greatest prime factor available within this numerical expression. The answer choice is number 13. Okay, so let's see another example. In question 4 says, for any integers x and y, the functions mean of x and y and max of x and y denote the minimum and the maximum of x and y respectively. For example, the mean of 5 and 2 equals 2, and the max of 5 and 2 equals 5. For the integers a and b, what's the value of max of a and b? Well, statement 1 says a is greater than b. Statement 2 says a times b equals -1. We need to be careful with this question because in this question, most people usually confound the concept of value with that of output. If you're supposed to find a value of this, what is this? Or what does this expression represent? This expression, max of a and b, represents the output or the result of evaluating the function max with the inputs a and b, according to the definition of the function max given above. But what is that definition? The definition is that the max of two numbers, x and y, is simply the greater of them, or the maximum of them. So clearly, they are asking you, what is the value of the greater value between a and b? First, you need to determine what is that greater value. And secondly, you need to determine what is the exact numerical value. Only finding which value is greater is not sufficient. In order to give a unique answer to this question, remember that value in the GMAT means number. It doesn't mean simply the result. So statement 1 alone is not sufficient. Why not? Because knowing that a is greater than b simply means that the output of this function, max of a and b, equals a, because a is the greater of the two numbers. But then with this, we would have only changed the original question into this. What is the value of a? Now that we know what the max of a and b is, what that output is, then the question would be, what is the value of a? But do we know what a means or what a is worth? No, we don't. We are told that a is just an integer, and an integer may have infinite values. So this answer is, we don't know. Actually, we could say a is 1. Who would contradict us that a is 1? Unless they give us the exact value of a, or a is 1 million, or a is any other possible integer or number. What about statement 2? Statement 2 says that a times b equals -1. Well, this looks like a and b are undetermined, or at least that's the concept if we don't know exactly what a and b are. But considering that a and b are defined as integer prior to the question, then that a and b multiply give -1 could mean either of just two cases. Either a equals 1 and b equals -1, or a equals -1 and b equals +1. No other possibilities may exist because a and b have to be integers. No other integers might have a multiplication of -1. So if we evaluate case by case to verify whether these different cases yield a different answer to the question, the main question, which is this, then in the first case, we would have that the max of A and B would simply be 1, because 1 is the greater of the two values. And in the second case, the max of A and B would again be 1, because if we compare 1 and -1, no matter in which order we compare the numbers, the greater of the two has to be always the positive one. So 1 is the unique possible answer to the question. What is the value of max of A and B? It's 1. Only if A times B equals -1. So this is a unique answer. Statement 2 alone is sufficient. A correct answer choice would be the second option. Okay, so be careful not to get carried away that you think that you know what a certain expression that invokes the definition of a function means truly. You might know the output of the expression. An expression like max of A and B always signals the output of a function. But be careful that not all outputs of functions are always numerical values. They might also be algebraic expressions. So let's see another example. Question 5. It gives us another definition of a function f. It says for all integers n, the function f is defined by f of n. This equality defines the function or the algebraic rule f. F of n equals a up to n, where a is a constant. That is a numerical value, but we don't know which one, at least for the time being. What's the value of f of 1? So we said again that when we see the name of an algebraic rule or function accompanied by whatever expression between parentheses, that always means the output of that rule whenever we give as input to the rule the value or the expression that is between parentheses. We would substitute this 1 wherever the variable n appears in the definition of this function. In other words, f of 1 means a up to 1. But a up to 1, any constant value up to 1 is just the same value. So based on the definition of the function, the question becomes, what is the value of a? So this is our true question. This is what we need to respond to. Let's see if statement 1 helps us give a unique answer. F of 2 equals 100. Okay, what is f of 2 as per the definition of the function? F of 2, according to that definition, would be what? Do you think? What expression results if we substitute 2 wherever n appears in the definition of the rule? Well, as the rule is a up to n, then a up to 2 would be the output of this rule with the input value of 2. So if we know that f of 2 equals 100, that means that a squared equals 100. But that a raised to the exponent 2 equals 100 means that a can be positive or negative 10. So this is not a unique value for a, right? Statement 1, not sufficient. What about statement 2? Well, as per the definition of function f, f of 3 would mean a up to 3. And if this equals -1000, then there is only one possible value for a that would make this equality true, and that is -10. Only -10 up to 3 gives us -1000. So we found a unique value for a, so the statement is sufficient. The correct answer choice is B. Well, those are some examples of how the definition of a function works in a GMAT Quant question. Let's now proceed to the second type of question in this lesson. The questions about operators are similar in logic to those about functions, because if functions represent algebraic rules that we name or label using, for example, a small letter such as F, G, H, or any other short words such as min, max, as we saw in the examples, then an operator is a symbol that also represents a mathematical rule, usually between two variables that represent two numbers. So the concept of operator means that you may be given any symbol that you might find on a keyboard, or perhaps other different symbols, such as, for example, the asterisk. If the asterisk, we want to represent a custom operation that is a special combination of algebraic operations between variables, we might say, for example, that we define the operation asterisk using an equality. On the left side of the equality, we would write what a typical operation with that symbol would look like. A asterisk B. This means doing the operation asterisk between the two values A and B. So on the right side of this, you would find the definition of the rule. A definition which would be an algebraic expression, compound algebraic expression, using the placeholder variables A and B to represent two numbers. For example, we might say that this operation means taking the square of A, the first number or the left operand, and add it with the square of the second operand or number that appears in the definition. Okay, so whenever we see something like this, it means that we need to pick numbers A and B, square each of them, and then add them together, those squares. That would be the output or the result of the operation. So following exactly this definition, what would be the result of doing these operations? 4 asterisk 1 asterisk 2. Well, we can simply use a definition each time the symbol with a special meaning appears. The most interior operation must be done in the first place. That is a typical criterion of the priority of operators and operations within a compound algebraic expression. So we'll do first 1 asterisk 2, the innermost operation. So 1 asterisk 2, as per the definition, would mean take the square of the first number, take the square of the second number, then add them together. And that would be the output or result of that operation. That is to say 1 plus 4. Okay, if we add 1 plus 4, that yields 5. So the original operation gets to be 4 asterisk 5, because 5 is the result of this parenthesis here. So now again, we apply the definition of asterisk. As per the definition, for asterisk 5 would be 4 square plus 5 square. We substitute each of these values wherever A and B appear correspondingly. And then we operate. This is 16 plus 25, which in the end yields 41. So the result of this sequence of operations is number 41. Well, in the GMAT, different symbols may be defined as special sets of operations or be considered operators. The most common place are, for example, a triangle. You might see a triangle between two numbers such as A and B, or two placeholder variables such as A and B or X and Y, etc. Another possibility is that you see an inverted triangle representing another sequence of custom operations. Then there are other symbols. For example, it's very common to see, for example, the add symbol, or perhaps the dollar symbol. It might be mean something. Or perhaps a symbol that is like a circle with a dot within, something like this, a custom operation. Another possibility is a circle with a cross within, or perhaps a circle with a next shape within, and so on. There are many others. Sometimes the operators are applied only to one placeholder variable. For example, you might see an operator like this, a square around a certain numeric value, okay, where A represents that numeric value. Or they might give you something like this, a triangle and a value within. Or perhaps one number followed by this symbol. Or perhaps it could be something that looks like a pair of square brackets. Perhaps this. Sometimes these square brackets are not given complete, are given only as two symbols, two vertical bars with a serif each, something like this, or perhaps this, the other way around, or perhaps a combination, something like this. Neither of these cases mean the absolute value, by the way. Okay, the absolute value is always this, right? Two vertical bars around on both sides of an expression. Well, let's see examples of some questions where the concept of operators is applied. So let's skip here to see question 2. It says the symbol, inverted triangle, represents one of the 4 operations of addition, subtraction, multiplication, and division. What's the value of 5 triangle 7? Statement 1 says that 1 over 5 triangle 1 over 6 equals 1 over 30. And statement 2, 0 triangle 6 equals 0. So would you say statement 1 is sufficient? It might look like it is sufficient because one feels that this could mean no other thing but the multiplication of 1 over 5 and 1 over 6. It's so obvious, right? But is this really the only possibility? Since the definition prior to the question says that the triangle may represent equally any of the 4 basic arithmetic operations, then at least we owe this to ourselves to try the other possibilities in order to discard the chance that there is more than one option or answer. What happens with a subtraction? Isn't it true that the subtraction of 1 over 5 and 1 over 6 is also 1 over 30? Well, if we do the operation, we realize that that is correct. 6 times 1 minus 5 times 1 over 5 times 6 exactly equals 1 over 30. It is not so apparent, you know, just looking at the expression. More apparent than the subtraction is the multiplication, but the fact remains the same. The triangle doesn't have a unique meaning because it might mean either of the two options. So there is not one unique value that we may give as the answer because it's not the same thing 5 times 7 than 5 take away 7. We would have two possible values for that expression. Statement 1 is not sufficient. So what about statement 2? If 0 triangle 6 equals 0, triangle means a unique operation, but it might be more than 1. Again, the most obvious one would be the multiplication, right? 0 times 6 equals 0. But if you divide 0 by 6, that also yields 0. Yeah, 0 is divisible by any number except by 0. The division by 0 is not defined, but 0 can be divided by any real number. 0 divided by x, always 0, whenever x is different from 0. So if we know this to be true, then again, the triangle doesn't mean a unique operation. So the answer is not unique either. Only when we say that the two statements are considered to be true at the same time is when the triangle, the inverted triangle, means the unique multiplication operation. It could mean no other. The only operation that makes true the two statements at the same time would be the multiplication. It's only the common choice in each of the statements, right? So the two statements together are sufficient, but not each statement alone. Correct answer would be C. But let's see another example. Here there is a rather challenging question. If, okay, exactly the operator I mentioned earlier, something like a square brackets. Okay, it's not the absolute value though. So let's call it square brackets. If a square brackets of x denotes the greatest integer less than or equal to x, that means in order to know this value, we need to know what is the value of x. We calculate the square brackets of x depending on this value according to this definition. The question is the square bracket of x equal to 0? And we are given two statements with two inequalities that establish the possible range of values for x. Okay, how can we analyze this without making it too complicated? Well, the best way is to use the definition to reinterpret the question given here. Since the square bracket means the greatest integer less than or equal to x, this question might be reinterpreted like this. Is 0 the greatest integer less than or equal to x? This question actually requires a yes or a no for an answer. How do we know if 0 is the greatest integer less than or equal to x? Well, let's see one statement at a time. We know that what the first statement says about the possible values of x is something that we can easily visualize on a number line. We have here the pivot values 0, 1, and -1. And that means that x might be any possible value in this range, without, of course, considering the ends of that interval. So if we cannot consider this possible value, neither this possible value, right? Any value in between is okay. For example, let's say that we pick this as the value of x, 0.5. This is our x. Let's ask the question about this value 0.5. Is 0 the greatest integer less than or equal to 0.5? Yes, it is. 0 is the greatest integer to the left of 0.5. So with this value of x, the answer to the question would be affirmative. Okay, let's try 0. If x were 0, is 0 the greatest integer less than or equal to 0? Yes, the answer would be affirmative again. Okay, so far so good. Okay, let's try a value here. For example, -0.5. If this were x, is 0 the greatest integer less than -0.5? Actually, no, because 0 is greater than -0.5. It couldn't be the greatest integer less than, neither equal to. So with this value, the answer to the question is simply a no. So clearly this is not sufficient. What about statement 2? Well, statement 2 says that x is less than 0. If x is less than 0, then we can visualize this on a number line, 0 here, a few pivot values. For example, negative integers, -1, -2, and -3. And we can continue assuming possible values for x. For example, x is this value here, -0.5. Is 0 the greatest integer less than or equal to x, that is to negative 0.5? Never, because 0 is greater. It's not the greatest integer less than negative 0.5. The greatest integer less than negative 0.5 would be negative 1. So the answer to the question here is a no. If we pick negative 1 as our possible value for x, 0 is not less than negative 1. So again, we have a no. And a value intermediate between negative 1 and negative 2, negative 1.5, what would be the greatest integer less than negative 1.5? Clearly, it would be negative 2. So again, the answer to the question with this value would be a no. If we assume that x equals negative 2, the greatest integer less than or equal to negative 2 would be negative 2. So again, the answer is no. We see that no matter which negative value we pick, 0 can never be the greatest integer less than or equal to a negative. So here we have a unique answer to the question, and that means sufficiency. Correct answer here is option B. Okay, so those are some examples about operators. Let us now continue with the definition of a sequence is a list of numbers where the values of the numbers in the list or in this special set follows a formation pattern. What kind of pattern? Well, we might be told that, for example, the nth term in a sequence, that is the numeric value in the nth position, is actually a function of the position of the term, a function of n. Example, if I'm told that we have this sequence where each of the values in their corresponding order n or position n is, for example, n plus 1 times n plus 2. So according to this definition, what would be the first term in this sequence? The first term in the sequence, or x1, would be 1 plus 1 times 1 plus 2. In other words, 2 times 3, or 6. The second term would be 2 plus 1 times 2 plus 2. In other words, 3 times 4, or 12. The third term in the sequence would be 3 plus 1 times 3 plus 2, that is 4 times 5, or 20, and so on. Using the rule of formation for a sequence, we can predict what is the numeric value of the terms in the sequence. The rule by which we determine the precise value of a term of a sequence is always a set of algebraic operations with the position of the term. Here we have another example. If x of n, that is the value of the generic term in a numerical sequence, equals 2 times n plus 1, then the first term would be 2 times 1 plus 1, that is 3. The second would be 2 times 2 plus 1, that is 5. The third would be 2 times 3 plus 1, that is 7. And we can realize that this means all the odd positive integers starting from 3. Okay, there are many possible patterns. Sometimes we can be given not a formula for the value of a generic term as a function of the position, but instead we define the value of a generic term in terms of the value of some terms that are in a prior position. For example, if we are given a sequence defined like this, the nth term in this sequence equals in value to 3 times the value of the term in the previous position, in the n minus 1 position, plus 2. So let's say that using this definition, we wanted to calculate what is the value of the third term. What is this using this definition? Well, if we use the definition, we would say that the third term has to be 3 times x sub 3 minus 1, that is x sub 2, or the second term, plus 2. But then, in order to determine what value is x3, we need to determine first what is this value. So we would have to use the definition again. x2 equals 3 times x1 plus 2. But now we need to know what is this value. Obviously, we need that first input. Otherwise, we cannot find the value of any term, because the first term should be the first in the set, the first element. So let's say that we are given that x1, the first term in this sequence, following this definition, is actually, let's say, 2. So using this value 2 here, we can calculate the value of the second term. We would say that this is 3 times 2 plus 2. That is to say, the second term is 14. Okay? Sorry, 3 times 2 is 6 plus 2 equals 8. 8 is the value of the second term. So what about the third term? Okay, you would have to multiply, right? 3 times 8 plus 2. That is to say 26. And in order, well, to find other terms, we would follow the same pattern. Here, the answer to the question would be the third term in the sequence is number 26. All right, so these are some of the questions. Usually, we might be asked to find the sum of a number of terms in a given sequence, or perhaps to do some operations with a couple of terms in a given sequence. Let's see some examples. Question 1. If a sub n equals -1 up to n plus 1 times 1 over 3 up to n, what's the value of a sub 3 minus a sub 4? Well, you can consider here that in this question, the difference of these two terms needs to be calculated over two numbers. So we need to determine the values of each of the terms. The third term, as per the definition, would be -1 up to 3 plus 1 times 1 over 3 cubed. If we simply substitute the position of the term 3 wherever the placeholder variable n appears in the definition of the sequence, okay? Likewise, for the fourth term in this sequence, we can do the substitution -1 up to 4 plus 1 times 1 over 3 up to 4. So if we calculate the values, this power here is -1 up to 4. So this is simply 1. Then the value of the term would be 1 over 3 cubed. But in the second term, -1 up to 5 means -1. And this would mean -1 over 3 up to 4. Now let's do the subtraction of the two terms. It would be 1 over 3 cubed, take away -1 over 3 up to 4. Give a common denominator, 3 up to 4, divided by the first denominator is 3, which multiplies the numerator. Negative and negative, this is an algebraic sum. So you have 1 over 3 up to 4. The answer would be 4 divided by 3 up to 4. Option 4. Let's try another example. Question 7 says, if a sequence is defined by a sub n equals n squared plus 2 times n for n greater than or equal to 1, what's the difference between the 9th and the 7th terms? So according to the definition, we need to calculate this, then subtract this. We're supposed to give this difference. Let's calculate or express the first term, a sub 9, in terms of a formula. It would be 9 squared plus 2 times 9, while a sub 7 equals 7 squared plus 2 times 7. If we do the subtraction of the two terms, it means adding these two and subtracting the two below. If we regroup the terms in this compound sum conveniently, we might have a difference of squares here plus 2 multiplied by the difference of 9 and 7. So this part is interesting. We don't really need to calculate the squares. We can simply use the identity that the square of a minus the square of b is a plus b times a minus b. So this is 9 plus 7 times 9 minus 7. And this is 2 times 2. While this is 16 times 2 plus 4. So 32 plus 4, 36. The answer is the last choice. Let's see another example. Question 8 says, if a sequence is defined by a sub n, the generic term in the nth position equals 1 over n minus 1 over n plus 1 for values of n greater than or equal to 1. What's the sum of the first 50 terms of the sequence? Well, we can consider what the result of adding a number of terms would be, especially the first 50, if we consider what each term looks like and try to see if we detect a pattern that would lead us to the answer of this question faster. For example, a sub 1 or the first term would be 1 over 1, 1 minus 1 over 1 plus 1, that is 1 over 2. While the second term would be 1 over 2 minus 1 over 2 plus 1, that is 3. The third term would be 1 over 3 minus 1 over 4, and so on and on. The 49th term is 1 over 49 minus 1 over 49 plus 1, that is 50. And the last term in this sequence is 1 over 50 minus 1 over 51. We are supposed to add all of this. Okay, resulting in this expression that has couples of terms that will cancel together. For example, these two will cancel together, these two will cancel together, also negative 1, 4 with another 1, 4 over here. Here probably a negative 1 over 49 with the following, and these two also. So in the end, when we do the sum, all of these pairs will get canceled, leaving us with just one, this part, and this term, which is not actually canceled. So 1 minus 1 over 51. Okay, if we do the operation, we get the value of our sum. Last answer choice. Well, that's it. This is the last example of this lesson. Let's move on to our lesson 14.